In the last video, we started to talk about the unraveled exact couple. And remember, our setup is that we have some filtration of space X. Maybe finite, maybe not. So we have some filtration, and for each of these inclusions, the p minus first filtration into the p, we get a long exact sequence in homology. And that'll be our connecting homomorphism, goes to xp minus 1, goes to the homology of xp, goes to the homology, the relative homology, and then our connecting homomorphism drops us down a degree, as usual. And for the sake of the unraveled exact couple, we're going to dive into it, and so I'm going to need names for these maps. So let's call these I and J. And I'm going to call the connecting homomorphism K. And of course, this is really an abuse of notation because there should be an I for every N. But I'm just going to call it all I, coming from this inclusion, which I'll also call I. So there's some abuse of notation here. And of course, this is exact. So that means that j after I is equal to 0, and k after j is equal to 0, and I after k is equal to 0. Just saying that it's exact. I mean, that's really just saying that d squared is 0 if we think of this as a differential. In any case. Okay, so let's get back to our unraveled exact couple. And I'm just going to paste the one that we had before, though you'll see I've now added another line. So I've included the homology of xp minus 3, and of course this continues, so really ... in all directions. Okay, and now we want to say how we get a spectral sequence from this. Well, at least we'll say part of the story. So where are we going to begin? Let's let E1 be HP plus Q of XP, comma XP minus 1. Remember, we said that we'd have a spectral sequence starting with that E1 page, so we're just going to define all of those PQ groups on the E1 page. But of course, for this to be a spectral sequence, we're going to need a D1. So what we're going to do is define D1 to be J after K. Now, of course, K after J is 0, right? So, okay, maybe I should put these labels. We've lost the other ones off the screen, so I was calling this I and J, and this connecting homomorphism is K. So that was all in the maroon sequence. But now I have the same thing really in the blue sequence. So by abuse, I'm going to call all of these induced maps from inclusions I. So I've got lots of I's around. And I'm going to go call all of these maps over J. Now if you want, you can be really careful and think of them as J with some subscripts. But I think the sort of, you get lost in the notation and it's easy to lose the point of what's happening. I'm going to call all my connecting homomorphisms K. Realized I missed a couple here. Okay, so then I've got some K there. Hopefully I've labeled them all now. Okay, so when I say I'm going to define D1 to be J after K, what I'm really doing here is this J after K, maybe let's highlight here. That is my D1, so that composition. Notice if I had done K after J, well then that would have been all in the same long exact sequence, and so of course that's 0 because my sequence is exact. But this J comes from a different long exact sequence than this K, and so those really are, potentially that composition is not 0. Okay, so we'll come back to this picture and I'll probably just have to scroll up because my handwriting is big, I guess. But that's going to give us D1 from E1 PQ. Well, let's see where it goes. Our D1 is this composition. j after k, and so it's going to go from, I guess maybe let me remind you off to the side, I'm taking n to be p plus q. Okay, and so this d1 goes from e1pq, which by definition is hp plus q of xp comma xp minus 1. I notice this composition lands me in hp plus q minus 1 of xp minus 1 xp minus 2. So I get different, there'd be a different filtration quotient if this is a nice CW inclusion. And I've also changed the degree of the homology. But this is something that shows up on the E1 page. This is E1, well, I guess P minus 1, comma, Q. And, all right, this got a little crowded. Let me see if I can clean that up. So this is a differential that goes to the left 1 and up and down 0. So yeah, that is the correct degree that I should have for my D1 differential in my homology spectral sequence. And D1 squares to be 0. So maybe let me say, notice D1 after D1, well, that's just JK, JK. Well, okay, that seems kind of silly, but remember these J's and K's are really all different J's and K's. So when I look back up in my spectral sequence, K after J always lives in some particular long exact sequence. So that KJ is just 0, and so this is 0. And so we have that D1 squares to be 0. That's also a good thing. And now, what are we going to do to keep our spectral sequence going? Well, we're just going to let E2 we'll define it to be the homology. So take the kernel of D1, mod the image of D1. Okay, and of course that means at the PQ spot, you take the kernel of the D1 going out of that spot, mod the image of the D1 that's coming into that spot. So going back up to my picture, maybe I look here, and I've got a D1 going out and a D1 coming in, and so I take the kernel mod image there. Okay, so this is some quotient of that first homology group, or I guess it's not even quite that because I'm taking kernel mod image, not the whole thing mod image. Okay, so now I want to define D2, right? So how am I going to get D2? Well, maybe let me first, I'm trying to decide whether I should first point or I should first write it down. Maybe I'll try to go back and forth. I hope this doesn't make you too dizzy. So let me say if D1 of something is 0, what does that mean? Well, D1 by definition was J after K. So J after K of A is 0. Okay, and what does that mean for us up here? Well, let's go back to our unraveled exact couple and put this little A in. And I guess I want another color to do that. Hopefully this one stands out. So let's start with A here. And it went over by D1 to 0. Well, if that's true, J after K applied to this A was 0, then really I could say that this A went to, I don't know, whatever K of A is here on the way, right? Because I applied J and then K. So this K of A is actually in the kernel of J. Okay, so K of A must go to 0. That's really the same arrow there. But I'm in a long exact sequence. Well, what long exact sequence am I in here? If you look here, I'm using the blue long exact sequence to apply J. And so if something goes to 0, there must be something that came before that hits it. So there must be some, let's call it B, that maps to K of A. Okay, so some lift of this. And now what am I going to do to figure out what D2 should be? I'm going to send B over. And so if A goes to 0, if it's something in the kernel here, then I'm going to lift, in some sense, this whole thing, and that will be my D2. You can see how this diagram turns into a mess very quickly. But just to talk through that again, I have this A that goes to 0. So there's something that's partway on the way. Let's call it K of A. That goes to 0 in this blue long exact sequence. So there must be a lift of it, B, up here in Hn minus 1 of xp minus 2. And I'm just going to send that B over, and then that, all of that sort of lift game, that's, maybe I should draw it like this. That's my D2 differential. Okay, so let me write some of that down because some people find the diagram chase more clear and some people find having it written down more clear. Let me give you both options. So remember, we started with this A that was in the kernel of D1 so that we could take something on the E2 page. And that means that J after K applied to A is 0. So we sort of just scaled back one stage of that and looked at K of A, and that's in the kernel of J. But as we said, the long exact sequence is an exact sequence. So there exists some B such that we apply I to it and we get K of A. Okay, so I'm going to scroll back up to our sequence. Now this vertical map here was I, and so I'm just lifting K of A back up that sequence. Okay, so there's some B there, and now we're going to define D2 of A to be J applied to that B, just as I wrote in the diagram. Okay, well, a lot of things need to happen here. So one is that we should have that D2 goes from E2 PQ to E2 P minus 2 Q plus 2 minus 1, right? That's just coming from the degree of our differential. And now E2, it's not just one of these homology groups in our unraveled exact couple, but maybe let me say this thing is related to something in our exact couple. It's HP plus Q minus 1 of XP minus 2, comma XP minus 3. Okay, so I'm just looking at where we landed in our unraveled exact couple, and we landed with something up here. Okay, so we started with something in Hn of xp comma xp minus 1, that's our E1 PQ, and we land somewhere over here, and I guess really at first that looks like something on the E1 page, but we want to land on the E2 page. Okay, so again, that's related to HP plus Q minus 1, XP minus 2, comma XP minus 3. Okay, and notice that the degrees there seem to check out. Okay, so this lands in the correct position. Because to form this E2 term, we should take something in the kernel of the D1, but from this homology group, mod the image, of course. Okay, so we're landing in the right spot, but why is D2 of A Well, I guess there are a couple of questions. Why is D2 well-defined? Why is D2 of A actually going to land in the E2 term and not just in this homology group in our unraveled exact couple? Where, remember, this is the kernel mod the image. And so there's a lot of things to check here. Well, let's check some of them. Okay, maybe let's start here. If we take this A to be in the image of D1, then I claim that K applied to it is 0. And so when we do this, this whole lifting game to find D2, well, we're just going to have K of A is 0. We can choose 0 to be our lift for B, right? We need some lift of it. Well, 0 maps to 0. And so then J of 0 will be 0, and that will be fine. So I claim that this tells us it's well-defined. Now I'm going to scroll back to our unraveled exact couple. I claim that if A is in the image of D1, then K applied to A is 0. So let's see if we believe that. Well, looking up here, if A is in the image of D1, that means something back here hit it. And now I took something from back here, I apply that to get A, and then I apply K, but now I've applied 2 successive things in the same long exact sequence. So definitely K applied to A will be 0. Okay, and so if I tried to start with this A and it was in the image of something, then I would play this game where I'd send it over and yeah, I get 0, but I might as well just take 0 here, that's K of A, and I can lift it back to 0, and so that's 0, and I send it over to 0, and so yeah, I'm just hitting something that's 0. Okay, just chasing zeros around. I'm going to scroll back down. We checked that this D2 is well-defined. Did we check that it was well-defined? I guess I still need to check that D2 sends A even to something in this E2 term, so something that's in the kernel, mod the image. So, but we certainly can define a map out of this thing. That's what we've now checked. So let's look at D2 of A. Well, this is J of B, where B is this lift. So if we look at D1 of J of B, meaning look at D1 applied to this thing, then we get J, K, J of B, but again, that K, J showed up together, so that's 0. And so this tells me that J of B is in the kernel of D1. So this map, D2, is mapping to things in the kernel, and it's taking things in the kernel here to things in the kernel here, and what we checked just before that is that if we took something that came from the image over here, it would have gone to 0. So that map is well defined. And at least now we see that we can define that map, and maybe there's more to do to check that we go to deal with the image there. But let me say there's lots to check. We also chose a lift B, so there's some diagram chasing to do. Let me just say I'll leave that as an exercise for you to play with. But I'm going to now scroll back to our unraveled exact couple and talk about how we deal with the next stage. So what we did here is we took an A, we said this composition, if that goes to 0, then we could just lift it part way, lift it back up the diagram, and send that over. Okay. Now for if that whole composition ends up being 0, then we can play the same game again. So we'll say, well, we really sent it over here to 0. So let's find something here, part way along the way. Really, we could just choose that B, and then we'll lift that up the diagram and send that over. Okay, so scrolling back down, let's write some of that down. So for D3, we want to do the same thing, same idea, and lift through I again. And now there's even more to check because on the E3 page, we have classes of classes, right? We've taken homology again, and so there's more to check. And the same idea here is to keep going so that our dr plus 1, I'm going to write equals in quotes because this isn't quite true, but basically what I do is I take, well, let me write it and then say. So I apply k, and then I lift up through I as many times as I need to, r times, and then apply j. So going back to the diagram, if I send something over and it goes to 0, then I'm just going to take it part of the way and I'm going to lift it up. And if I send that over and get 0, then I lift it up. And I send that over, and if I get 0, I can lift it up and keep playing this game. And so that's my dr. Okay, so again, there's a lot to check here to make sure that that's all well defined and mapping to the right places, but I'll leave that as an exercise. Notice I put this equals in quotes because there may be some choices of pre-images here, and also because once we get to the E2 page, we're not even actually lifting up this diagram. So we sort of are, but I really need to be looking at the quotients, all these kernel mod images, and playing with a diagram of those, and that's all sort of tedious to write down. But this is essentially the idea. Oop. Okay, let me stop this video here because I think that's kind of a lot. And I want to sort of just draw an example and say a little bit more about how this works for now.